All right, folks, we are now going to talk about significance testing for the slope of a regression line. So when we're trying to do a significance test for the slope, our hypotheses, our null hypothesis is that beta equals 0. Beta equals 0, or the slope equals 0. Okay, the null hypothesis can range from beta does not equal 0 to beta is greater than 0 or beta is less than 0. This would be saying that there's a positive correlation. We're suspecting that there's a positive correlation. And this would be that we're suspecting that there's a negative correlation. Okay, so the t-test for a regression, you can find that t-value by taking the slope minus a predicted slope, or the population slope and the sample slope. There we go. Sample slope minus population slope over the standard deviation, standard error of the slope on a roll. Okay, so let's go ahead and take a look at this thing. All right, infants who cry easily may be more easily stimulated than others. This may be a sign of a higher IQ. Child development researchers explored the relationship between the crying of infants 4 to 10 days old and their later IQ test scores. A snap of a rubber band on the sole of the foot caused infants to cry. The researchers recorded the crying and measured its intensity by the number of peaks in the most active 20 seconds. They later measured the child's IQ at 3 years of age using the standard IQ test. So a scatter plot and Minitab output have been provided here. So do these data provide convincing evidence that there's a positive linear relationship between crying counts and IQ in the population of infants? So I'll try and keep this on the screen a little bit here, and it'll have to go away in a sec, but that's okay. All right, so here's my B, here's my standard error of B. Now, what we are testing for is if there's a positive relationship between these data. So our state. We wish to test the following hypotheses. At alpha equals, does it say? Nope, I don't see it anywhere. So I'm gonna go with 0, 1, just because that is what my notes have on there, so I'm gonna stick with that. Okay, at 0.01 significance level, where the null hypothesis is that beta equals 0, and the alternative hypothesis, wow guys, is that beta is greater than 0. Where beta is going to be the population slope between baby cry counts and IQ. When they're 3. Okay, so let's go ahead now and plan. So I'm going to scroll up a bit here. So if conditions are met, we will perform a linear regression t-test for beta. Or you could just say slope. So our conditions, remember, are linear. These are what we want to check every time. So L, if we go back, L stands for linear, I for independent, N for normal, E for equal variance, R for random. So kind of keep that in mind as we go through this. E is so unfocused. That's a little bit better. Okay, so linear is the relationship between X and Y linear. So we need to assume the population data was roughly linear. All right, independence. So we can assume that individual babies are independent. Like their IQ and cry times aren't going to influence each other. And there's more than 38 times 10 equals 380 babies. Okay, for normal, like once again, we'll just kind of assume that IQs are normal. So we need to assume babies were chosen from a population with normally distributed IQ. All right, next, E stands for equal variance. The standard deviation of Y is the same as X. So we need to assume the standard deviation of any cry count data is the same as the standard deviation of the IQ test data. All right, and last is R, so it's linear without an A. And this is random. So it does, in fact, say we had a random sample of 38 infants. So we're making a lot of assumptions as we go through this. We're assuming that all these things are true, but every time we do have to note that, yes, I am assuming all these things are true in order to run this. Okay, so now we must do this in black so it'll show up a little better. I was going to do orange. But... All right, so now we're going to do. So we know going back up, which you can't see, but we're just going to roll with it. So B was equal to 1.4929. B naught, we're assuming, is 0 because that's my null hypothesis. Okay, the standard error of the slope is once again on that Minitab output, and it is 0.4870. And now our degrees of freedom is our sample size, which was 38 babies minus 2, so it's 36. So to find my t-value, I take my observed slope minus my predicted slope all over the standard deviation. I keep saying that, I'm sorry, the standard error of the slope. So in this case, that is 1.4929 minus 0 all over 0.4870. So this gives me a t-value, 1.4929 divided by 0.4870, and that gives me a t-value of 3.07. Now, we are interested in beta being greater than 0. So I'm going to figure out, all right, for my t-value, what's the probability that t is greater than 3.07? And in order to do this, we could use our t, here, let me. So we have 0, 3.07. This is what we're interested in. So it could be 1 minus the probability that t is less than 3.07. Or if we're just smart, we could use a t-CDF with a lower bound of 3.07, upper bound of 1,000, and degrees of freedom of 36. So when we do that, we get a p-value. I'm going to keep it up here actually, of 0.002. The last thing we got to do here is conclude. Oh, and I'm sorry this is in orange. I know that's not the best thing to write in. So we would say since a p-value, just ignore that other part, is less than alpha, 0.002 is less than 0.01, we reject the null hypothesis. We reject H naught and conclude there is a significant difference or not a significant difference, there is significant evidence to show a baby's cry count and 3-year IQ have a positive linear relationship. All right. And that would be our conclusion. That right there is a dang good conclusion. All right, so that pretty much sums it up for us, folks. So I will get the homework posted right after I post these videos. So make sure that you get on that. If you have any questions, just join that group discussion and I will answer any questions you have.